I'm going to tell you about field theories in condensed matter physics. I give a title of my lectures as Effective Field Theory in Condensed Matter, which is probably an oxymoron because we now think that, at least theorists think that everything that they are doing are effective field theory in particle physics. Every field theory we know is probably a effective field theory. And it's more so in condensed matter physics. But I'm going to try to emphasize some aspects of, of effective field theory that we wish that we have as a description of all physical systems. My first lecture is going to be on superfluid. And the second and third lecture, I hope to tell you about Fermi liquid. These are two classic paradigms for gapless condensed matter systems. The theory of superfluid is a very old subject. Helium-4 was observed to be superfluid by Kapitsa and other people, and Landau constructed this. In essence, the theory that I'm going to describe here is the theory that Landau constructed in 1941, 1 or 2 years after he was released from prison. So most of the things that I'm going to tell you are pretty trivial, although there are not a standard textbooks that would deal with non-relativistic field theory, but there is a chapter in Atonizi's book that covers some of the things that I'm going to talk about. The more non-trivial part of the talks are have origin in the paper from 1989 by Greiter, Wilczek, and Witten, and we also elaborated on that with Matt Wingate in 2005. Okay, so let's start with bosonic superfluid. Though superfluid behavior can exist also in fermionic system if we have Cooper pairing. But for simplicity, let's start with a system of bosons. And for simplicity even, let's start with weakly interacting bosonic system. Whose Lagrangian I'm going to write down. If the letters are too small, let me know from the back of the room. Is it okay? Yeah, thank you. Yeah, psi dagger I dt plus grad square over 2m psi minus g over 2 psi dagger psi plus mu psi dagger psi. So what's here? The kinetic term in the Lagrangian is dictated by the dispersion relation. Omega equal p square over 2m. Okay, this term is the interaction between the bosons. And for simplicity, I assume that the boson interact through a contact point-like interaction with coupling constant equal to g. This g is related to the scattering length between the bosons by a formula, which I write here. We are not going to need it, but it's good to have in mind that g is something that in principle is related to the quantity that can be measured in scattering experiment. And mu is the chemical potential. Okay, so what's written here is this part is, well, except for the, if you delete the time derivative, you would get the Hamiltonian density. And this is the Lagrangian density. Okay, so now let's look at the behavior of the effective potential. So the effective potential in psi is formed by terms with no derivatives in the Lagrangian. So in this case, it is equal to minus mu psi square plus g over 2 psi to the 4. Okay. And now we can plot this effective potential as a function of psi. Okay, clearly if mu is larger than 0, we have a situation where mu is smaller than 0. We have a potential that has only one minimum. If mu is larger than 0, then we have a potential with a minimum at value of psi. So mu larger than 0, minimum at value of psi equal then square root of mu over g. Let me delete this absolute value and write psi equal that e to the I phi. Physically, what happens is the following. If we have chemical potential that is less than 0, then in order to put in a particle in the system, it would increase the free energy. The free energy is, one have in mind formula for the free energy. Free energy is Hamiltonian minus mu times the number of particles. So if mu is less than 0, putting in one particle would increase the free energy. It's not very favorable. But if the chemical potential is larger than 0, it's favorable to put in more and more particles until the interaction between the particle stabilizes the system at this value of the field. Now, the density is psi Decker psi, and so density would be equal to mu over g in our case. We have spontaneous symmetry breaking. That means that the Lagrangian has a U1 phase rotation symmetry of psi that is spontaneously broken by the condensate. Particle number U1 is spontaneously broken by the superfluid condensate. So whenever I say superfluid, I will mean the state of matter in which U1 particle, there's a U1 symmetry that is spontaneously broken. When we have a spontaneous breaking of symmetry, we expect a Nambu-Goldstone boson, which will be the only gapless mode in the infrared. So we want to write down the effective field theory for this mode. So in order to do that, I'm going to separate my field into something that one expects to be gapless and something that one expects to be gapped. It's the same separation that we do in the Higgs sector in the standard model, that which we write psi. Let me write it to be equal to square root of n. So in this case, I use slightly non-standard notation for the absolute value of psi. This is motivated by the fact that psi square is equal to n. And so square root of n times e to the I phi. Phi is the Nambu-Goldstone boson, for which we want to write down the effective action. And the radial, the magnitude of psi, we expect that to be something like a Higgs boson that would be gapped. So what happens if we put this into the Lagrangian? So I'm going to write down what one gets at the end. So we get the following terms. So minus n dt phi minus n over 2m gradient of phi square. And then some other term that I'm going to write down for completeness, and minus g square over 2n square plus mu n. Okay, so this is straightforward. You put in there, and now I'm going to expand n around its expectation value n0. N0 is computed there, so this n actually is n0, mu over g. And then I put it into this Lagrangian, and one can get something like this. So if I follow the algebra, I find after straightforward, slightly boring calculation, you get something like this. Grad phi square plus minus G over 2 delta n square plus dot dot dot. I'm going to leave you the task of figuring out what these dot dot dots are. They are not, either they are higher order in fields or they are higher order in derivatives. We are going to concentrate on this term. So first of all, the first term is n0 phi dot. Okay, so I'm going to be naive or straightforward and declare that this term is a total derivative and ignore it. Okay, it's not really, there are some interesting effects that comes out from here if we treat the problem more carefully, but I'm going to ignore it. And now I'm going to look at this and say I can integrate over delta n, right? And then get the following Lagrangian. Delta n, there is one, I think I get, let's see, if I get one term, there is one term that I want to write here, 2m at phi square. I put in one term that I ignore my, my previous pledge to keep only a quadratic term in the Lagrangian. I put in one cubic term in the Lagrangian. You'll see why I want to do that. So integrate out delta n. So delta n appears as in the quadratic level in this Lagrangian. We can integrate out delta n by certain point. So certain point integration of the fluctuation of density give us the following effective actions. So delta n settled point, delta n settled point is equal minus 1 over g phi dot plus grad phi square over 2m. And then what I get is the following. The Lagrangian is minus n phi dot minus n naught phi dot plus grad phi square over 2m plus 1 over g 2g phi dot plus grad phi square over 2m square. Okay. Okay, again, I run it. Again, I keep this actually n0 phi dot term, though this is just a total derivative. Okay, so if you now look at this Lagrangian and ask what are the really important quadratic terms, the quadratic terms come first of all from this n0 grad phi square and phi dot square. So at the quadratic level, you get 1 over 2g phi dot square minus n0 over 2m grad phi square. Okay, so this is action of a massless scalar, basically what quadratic term with two derivatives, both in space and time, and it describes the superfluid phonons. The phonon propagate with a velocity that one can compute. So the dispersion from here, we get the dispersion relation omega square equal cs square q square, when cs, the speed of sound, is equal to square root of g and naught over m. Everything is very straightforward, and everything is as simple as the treatment of spontaneous symmetry breaking and complex field theory as you would treat in textbook, except there is one difference. There is no Higgs boson here. The fluctuation of delta m of the density does not correspond to any gap mode in this model. And the reason why we are missing one mode is because the original Lagrangian with which we start the calculation is first derivative in time. So instead of two different modes correspond to the real and imaginary part of the field, these real and imaginary parts are complex, canonically conjugate variable to each other. So there is only, at the end we get only the Nambu-Goldstone boson, but not the gap Higgs boson. Okay, so that's explained in why this is explained in Tony Z's books in quantum field theory. Any questions so far? Okay, so this is an exercise we can do in weakly coupled bosonic superfluid theory. But if we want to understand more realistic system, for example, superfluid helium-4, then this is only a sketch of what would happen there. The atoms of helium-4 interact strongly with each other, so there is no small parameter with which we can use to do this calculation. So in order, it's a different exercise to estimate where this calculation is reliable. But at the end, what we get is that this calculation is reliable. The derivation is reliable in the dilute regime, the regime where n(a) cube is much smaller than 1, n0. So when we expand around density, that is dilute compared to the parameter, the scattering length, which characterizes the coupling constant in the system. Okay, so now we want to understand strongly interacting superfluid. So the prime example is helium-4. It's a theory, we want to understand it. So clearly, with this system, we cannot start with a microscopic theory and derive everything that we want, but we have to follow the usual route in effective field theory, that is, we understand what are the symmetries that we have and write down the effective theory that respects all the symmetry. Using the fields that we expect to appear at low energy. Since we are dealing with superfluid, we still expect that there is the only fields that appear in the theory is the Nambu-Goldstone boson phi, the phase of the condensate. The condensate may be strongly interacting. Its phase should be the relevant low energy degree of freedom. So we want to write down a Lagrangian as a function of phi, the action as a function of phi, or Lagrangian as a function of phi in its derivative. Okay. Okay, so what are the symmetries that we expect here? We expect trivial symmetry translation. So translation in terms of the phi field means that if I take phi and shift the coordinate, then t prime equal t, x prime equal x plus a, then the theory, the Lagrangian must be, the action must be invariant. Similarly, I will require that there is a rotational symmetry and time translation symmetry. I require that the system has a U1 symmetry. So U1 symmetry rotates the phase of the microscopic bosonic field, psi there. But here it will, because phi is only a phase, the symmetry, U1 symmetry, map phi into phi plus the constant. Let's call that alpha. Alpha is a constant. U1. It has a shift symmetry, phi constant. And for now, I'm not going to distinguish U1 from R. I'm going to just require shift symmetry. The more non-trivial symmetry that we want to impose into the theory, if we wanted to describe helium-4, is Galilean boost symmetry. And this one is actually turned out to be a subtle thing to describe. There are various ways to understand how the phase of the condensate must transform under Galilean boost. One way is to appeal to the original, to this microscopic Lagrangian. So the microscopic Lagrangian here, if we have a real, if we want to describe a real helium, we have to replace this term by some more complicated term that describe the real microscopic interaction between helium atoms. So to look something like this, dx dy, psi dagger x, psi dagger y, some potential x minus y, psi y, psi x, where this potential has to be fit to the von Oppenheimer potential between two helium atoms. That looks quite complicated. It has certain shape like this. All these details we need to know if we want to really do microscopic calculation, but here we want to understand just a symmetry. So we can ask what kind of symmetry this Lagrangian have when we try to boost psi, want to try to replace psi at t of x to another psi which at x plus vt equal to the previous psi. So we can ask whether this would be the symmetry of the action. And you see, when you try to put it into the action, you see right away it doesn't work for the following reason. If I now take the passive point of view on the Galilean transformation, that is the new field is equal to the old field computed at x minus vt instead of at x. When I put that into the action, the time derivative in here acts on the second parameter of the psi and then give me a mu term that is not cancelled by anything here. So Galilean symmetry actually is more subtle, and you can check that this problem can be solved quite easily by inserting a new a phase into the transformation. This phase looks something like this: m x dot v. I'm not going to pretend that I remember the signs right, but I think it looks something like this. Okay, so it's just you do by trial and error. You can find the correct transformation of the theory under Galilean boost symmetry. So actually, as we expect, the theory of helium has a Galilean boost symmetry, though the transformation law is a little bit subtle. And so if we now look at the transformation of the field phi, which is the phase of psi, we can expect that to be phi going to transform at t and x, going to transform like t at x prime equal 5t of x plus these things, x v dot x, and then minus p squared over t over 2, something of this form. Any questions so far? This is the first thing that might be not familiar with most people, with some people here.
Then that should transform as a constant under Galilean boost.
Yeah. So you'll see here the constant appeared because the derivative here as an m. Actually, I'm missing this m here now. This m here. So the superfluid velocity again is gradient of phi divided by m, and you see the superfluid velocity shift by v as it should. So it's another way to see that in the transformation for phi under Galilean boost, there must be a term linear in x. So that is something that that we need to impose. Okay, so once this is done, we can go back to the action and ask, how do we make sure that the action that we write down has this symmetry? So this Galilean symmetry, this question was asked by Greiter, Wilczek, and Witten. And if we now try to construct the effective action respecting this symmetry, we find the following, that the Lagrangian can be written as some function, let me say, some function of the following quantities that I write: phi dot minus 1 over 2m grad phi square. Okay, and this is any function. It can be any function of the argument. One can check that this, if we take this, it will be invariant under Galilean symmetry, because what stays inside the function is a Galilean invariant quantity. Yeah. So here I'm have to ask what things have been included here and what are not included. So included in here are the following terms. Because this can be any function, including quadratic, cubic, quartic, etc. If I expand it out, I get all terms of order. This contains terms with any power of phi and any number of derivatives summing up to n. So it's n1, n minus n1. I write it only schematically. That is, it's any term like this will contain terms with the number of derivatives equal to the number of fields. Okay, so why is it so? Remember that the theory has to have shift symmetry. Phi goes to phi plus alpha. So the field phi cannot appear individually in the action without in the Lagrangian without breaking shift symmetry. Phi always has to appear with the derivatives. So if I have n phi, n factor of phi, each of that has to come with at least one derivative. And this Lagrangian summarized all terms with the lowest number of derivative at each power of phi. Okay. Any question? So the term that has higher derivative ignores terms like d phi, or d phi square, etc. Terms like that are ignored in this action. Okay, so now there is something interesting about this symmetry that I want to tell you. In fact, this is not the way that Greiter, Wilczek, and Witten derived this action. In fact, what they did was to require a condition, a different condition on the action. They say that in a Galilean invariant theory, so this word is already used. In a Galilean invariant theory, they say the following condition must be satisfied. Let me write this. di0 equal mji, and then explain. T0i is the momentum density. This is the quantity that appear in the conservation law for the momentum. And this is the U1 current, particle number current. This is the current that appear in the equation of conservation of current, of U1 current. In helium-4, if an atom moves, it carries a momentum, but it also carries a current. It also has a current. And in a Galilean invariant theory, those two things are tied together. So here we see something quite non-trivial. If we write down a random effective field theory of a field, the Nambu-Goldstone boson of U1, requiring only the U1 symmetry bracket, U1 shift symmetry, we will not satisfy this condition. In fact, this condition requires, if the Lagrangian is only a function of phi and its first derivative, then it's required that dl over d0 of phi, di of phi is equal to dl, let's see, dl over di of phi m. Right. In fact, you can check that this is correct for the microscopic theory that we wrote down here. You can check that dl following the Noether rule for the momentum density and the U1 current. You can check that the Lagrangian that we wrote down up there, I'm not going to write the condition here. The Lagrangian we wrote down here satisfy this, this requirement. But the requirement becomes non-trivial when we go from the microscopic theory to the effective theory. This relation can now be solved. This equation can be solved, and the solution is this one here, up to a sign. I'm not sure I get all the signs right. Okay, here you see something quite, any question so far? Yeah.
So I was just wondering, so up to the step that you have done here, right? In principle, I could also do it if I replace the first term in the Lagrangian with Klein-Gordon. So you can do this for relativistic theory also?
For relativistic theory, we don't have the condition that momentum density is equal to U1 current. Yeah, actually, there is a separate story in a relativistic superfluid. The requirement there is easier to impose, the requirement of Lorentz invariance. Yeah.
So, in the macroscopic theory, we have five-dimensional part two, but then here five into active, we have five dot one so I wonder how make this difference.
You mean in the relativistic, in the microscopic theory, we have derivative?
No, so we have five dot plus R2.
Pi dot?
R2, five dot square.
In the effective theory, we have pi dot squared to the power of 2.
Yeah. But then here we only have a five dot.
Yeah, let me mention that later.
Okay.
When I linearize, when I extract the quadratic terms in here, in this section. Any questions about? No. Yeah. So this Galilean invariant theory has this. The action has to be Lagrangian. Now depends on an arbitrary function of its argument. So what is that function? Now one can ask. Can we measure this function? And it's turned out that this function actually it's completely related to the equation of state or the thermodynamic properties of helium-4 at zero temperature. So here is the claim that I'm going to give you this without proving, but then I'm going to do certain calculation and show you that this claim is reasonable. The claim is that this function P, yeah.
Symmetries were manifest.
Yeah.
And you did just a change of variables. You did not neglect anything. So how come you need something more elaborate? Where did this thing enter?
No, but we see here already, if we, in the case when we could do all the calculation step by step, the result does look like the expansion of this function to first and second order. Yeah, so what we are saying here that the symmetry doesn't require that this function to truncate at quadratic order, but this series can.
I can see why the middle board is consistent with the left board.
Mm-hmm.
On the right board, you said that there was an issue, and that's why this is how you motivated the left board.
What was the issue? The issue, this one, is that we need to make sure that the Lagrangian is invariant under this symmetry. And it's not exactly straightforward that anything that actually not true that anything that we write with this phi is going to have this symmetry. This symmetry looks somewhat reminiscent of what people now would be called a dipole symmetry. But here it just has a meaning of the Galilean boost symmetry.
Momentum is equal to the U1 current, right? So does it mean that the translation of the U1 symmetries are not independent symmetries?
I'm going to mention that. That's one of the things. I hope to have time to say what's really happening here. They are not, independent in a certain way of viewing the problem.
You wrote something that's like the momentum density equals to mass times the current. Where does that come from?
It comes from the, you can see that like this. You can, first of all, you can see that from the microscopic theory. When we compute the momentum density, so the momentum density in the microscopic theory has the following form. If I'm not wrong, I think it's something like this. Psi Decker, di psi Decker minus dl over d0 psi di psi. Okay, and then if you do this calculation, being careful with the fact that in order for the Lagrangian to be Hermitian, you need the derivative to act both on psi and psi Decker. You compute directly and you find this equal minus I, something like psi Decker di psi minus I over 2 di psi Decker psi. So first of all, by direct calculation, you can see this one is m times the current. But you can also see that at the classical level. Imagine that you have just a collection of particles. So each particle moves with a velocity v, roughly speaking. Then inside this volume, you have the momentum density equal to rho times v, right? Rho times v. Rho is the mass density times v. While the current, so this is a momentum density. And the current density is n times v, where n is the particle number density. The mass density is equal to particle number density times m. That's where this formula comes from. Yeah.
Are these forbidden by symmetry or just more than?
No, I just no. If you write them down, you have to think about the symmetry, and the number of terms allowed by the symmetry is less than the number of terms one can write down without thinking about the symmetry. So the symmetry actually also imposes certain requirement for term with higher derivatives that I'm not writing down here. At the level of the basic term, leading term, all the requirement boil down to a arbitrary function. You can have only a function. Okay. So the claim that I'm going to make now is that this function, yeah, you have a question?
Equation with relation between the momentum density and the current holds in a Galilean invariant theory. Where did you use like the Galilean invariance?
Yeah, so Galilean invariance is needed to fix the form of the Lagrangian. If we have no Galilean invariance, let me say, if no Galilean invariance, we would have a Lagrangian, which can be any functions of derivative of t and gradient phi square, requiring only rotational invariance, U1 symmetry, translational invariant. We have a function of 2 variables instead of a function of 1 variable like this. So Galilean invariance allows us to reduce everything to 1 function, which and this function turned out to be a physically measurable function. And the claim is that this function P is the same function that gives us pressure as a function of chemical potential. Okay, something that in principle one can measure experimentally through helium-4, for example. So naively, at the hand waving level, chemical potential can be thought of as the rate of rotation of the phase of the condensate. So the phase of the condensate and the particle number are canonically conjugate, and then inserting a mu n into the Hamiltonian rotate, make the finite rate of rotation of phi. So that's how one can see this argument here has to have the physical meaning of the chemical potential. Now, the Lagrangian is the fact that the Lagrangian is pressure. It come out from field theory. Usually, when we compute the pressure, the expression in the pressure always involve one term that is Lagrangian. Okay, so but the real proof has to be more complicated than that. I'm going to assume that P is this function is the same function determining P as a function of mu, and then compute, for example, the speed of propagation of the superfluid phonon, the quantum of phi. Okay, so if P is a function of mu, what we expect? So P as a function of mu, we have to expand this around the background of finite chemical potential, right? So we have helium-4 existing at the finite chemical potential. So we expand phi equal minus mu t plus delta phi, right? And then the Lagrangian becomes pressure evaluated at mu minus phi dot minus grad phi square over 2m. Okay. So let's expand this in Taylor series. So mu here is a constant. So let me write it's mu 0. We are doing perturbation theory around a state with a given chemical potential. P at mu 0 minus dp at d over d mu at mu 0 phi dot plus grad phi square over 2m plus 1/2 dp square over d mu square phi dot plus grad phi square over 2m square. Okay. Now, the first term is that this is constant, so we ignore dp over d mu. So there is a relationship in thermodynamics. dp equal, I think, something like minus s dt or plus s dt plus n d mu. N is the particle number density, temperature is 0, so nothing appear here. We have only n d mu. So this one is like minus n. N is the density, which is here just a constant. Minus n phi dot minus n over 2m grad phi square. And here I have dp over d mu. Okay, so I keep it like that, plus half dn over d mu. I'm sorry, dp over d mu square is dn over d mu phi dot square plus higher order terms. Okay, so I need some more space to write, so I do it here. From here we find the velocity of the Nambu-Goldstone boson square. So this term again is also a total derivative. So the term that determine the dispersion relation are only these two terms, and the velocity then is n divided by m divided by the coefficient in phi dot term dn over d mu. So I can, using certain thermodynamic relation, one can rewrite this as derivative of pressure over the density. Okay, so this is the familiar formula for the speed of sound in the usual medium, like air, for example, except in a finite temperature system, a speed of sound would, we have to specify that this derivative is computed along adiabatic curve, that is that constant entropy per particle. Here, there is no entropy, temperature is 0, so the density determines completely the pressure, and the formula for the velocity is just the usual velocity in the normal, in the usual fluid. So it's one way you can see that it's reasonable claim that this function is just determined by the equation of state of the substance under consideration. Any question so far? Yes. Phi equal to? Why is it so? Okay, so here there is some things that when you have the Hamiltonian, that it is there is two different way to evolve operator, either with the Hamiltonian that includes the mu times n term, or without the mu times n term, and they differ from each other by the rate of change of the phase of the condensate. So here I'm choosing the I think the convention in which the time evolution is determined by the Hamiltonian without the mu n term. Okay. In fact, here it's basically a convention. You can, in order for the P to be the function of chemical potential, I make this convention. Otherwise, it would be P as a pressure as a function of chemical potential minus mu, minus some constant, which is a little bit less convenient. Okay, so there was a question. Yeah.
This Lagrangian get renormalized? Or can M in this Lagrangian get renormalized, or is it always like the bare mass?
Can this Lagrangian be has a renormalized? So this should be understood as an effective Lagrangian. That is the Lagrangian that is not that contains in principle, infinite number of terms. So now there is all the terms that beyond the quadratic term, you can do a power counting and convince yourself that these terms are irrelevant. So so in order to compute certain quantity, you have to use this Lagrangian as an effective Lagrangian.
Normalized.
Oh, the mass. The mass in this Lagrangian cannot be renormalized because it's something that appears in the transformation law, in the symmetry, in particular you can trace it back to the commutation relation between Galilean boost and translation. This has a well-defined coefficient, and this coefficient cannot be renormalized. Yeah. Okay, so now let's go back to this very strange relationship that is, yes.
I could do everything at the starting point that you had about. And there I would have guessed that this M is renormalized.
But not in the infrared.
Yeah.
This M here is the same M. So in this M here determined by various things that cannot be renormalized.
They're inside.
And inside here is the same M. So
Can this be renormalized?
this M here? Yeah, depending on what you mean by renormalized. If you next time I'm going to talk about the Fermi liquid. In a Fermi liquid, there is a notion of effective mass that can be renormalized, but there is this relationship between the in a system with Galilean invariance. There is certain combination of this renormalized mass and coupling constant that has to be equal to the bare mass. So in this case, in the superfluid, it's hard to point what observable would give you what one can call the renormalized mass. There's no such thing in the infrared.
Equals MB to derive that the Lagrangian is a function of this combination. Can you do something similar in a relativistic theory?
Yeah, in the relativistic theory, the thing is this would be P and then square root of the mu phi square. Actually, in the relativistic theory, it's again another function P as a function of mu, but the argument is square root of the mu phi square. Okay, so now what is the symmetry, the nature of which has been, the strange nature of which has been noticed, that it's somehow tied up two different quantities that usually we think about as appearing from two different symmetries. One is the U1 particle number symmetry, and the momentum density should be considered as part of a certain, usually we think about that as part of a stress tensor that comes out from the Gibbs invariant. Okay, so in a relativistic theory, it's very easy to couple the theory to the metric, and differentiating the metric, we get the stress tensor. It's not that straightforward to do it here, because if we try to write down coupling to the metric, most natural metric that appear in the theory would not be the space-time metric, but only a spatial metric, because we have term in the Lagrangian grad square over 2m that can, the only thing that we can attach the metric to. So if we try to write an action that looks like this, we can, the only natural metric we can turn on is the spatial metric. So let's try to think about like an action of a particle that interact with U1 gauge field and a metric. like this. Plus dot dot dot, and these dot dot dots are potential interaction between particles that depends on the distance of the part between the atoms, and this distance also has to be measured with respect to this spatial metric. Okay, so now we can ask what are the symmetries of this Lagrangian. So we have U1 symmetry, of course, the rotation of psi. Gauge symmetry, psi goes to e to the I ei psi. Where alpha now can be a function of x, and that can be compensated by gauge transformation of a mu. And we know that this is the origin of the conservation of current. The mu j mu is equal to 0. Okay. Now, this one, it turned out that it has the following non-trivial symmetry. So first of all, there is a time-independent div. When we take psi and make it into psi minus c I di psi. All right, let me write it like this. The change of psi is equal the Lie derivative of psi with respect to certain gauge field xi, that is the gauge field parametrizing diffeomorphism, change of coordinate. Now if we do that, combined with delta gij equal the Lie derivative of the metric with respect to this gauge field, then this term, and then we assume that all this AI transform also like that. And if psi is only a function of x, not time, then obviously what we wrote down there is invariant. But it is not an invariance that gives rise to this relation. We can check that if we make this a function of time, diff, we consider a diff that change the spatial coordinate on each time slice in a way that depends on time. The Lagrange, the action is still invariant if one makes the following modification. So this one is quite it's actually quite natural because a mu we expect to transform like by a vector. This one remains the same. This one remains the same. This turn out to need this modification to make the action invariant. Okay, so here it's just an experimental fact. We put everything in and we get the symmetry that comes out. It's a strange symmetry because, I'm sorry, minus m gij psi j dot. Psi j dot. Gij? Gij is the symmetric. Very strange because in the transformation for the gauge field, there is that metric that appear in them. I should write it a little bit. Has a what? Metric, the spatial metric has determinant non-zero. So, but there is only spatial metric. There's no G00 or G0I component that we turn on. So this, let me write again, this minus AI and minus M Gij G dot. So it's this metric is can be inverted. This, in the Lagrangian we have the inverse metric, and here we have the metric with lower indices. Okay, so this is what we can actually now repeat the calculation, requiring that the effective field theory can be coupled to the external gauge field in such a way that this the resulting theory satisfy the symmetry and rederive everything that we have done before. We got back this Lagrangian. We rederive basically Greiter will check in Witten result, but with the use of a strange symmetry that mixes U1 and the metric. So in this sense, I think Galilean symmetry in somewhat special, in the sense that if one try to rewrite one of these relationship as a Watt identity, one definitely need to make the transformation laws for the metric and the gauge field to be intertwined with each other. In the bosonic theory, that's quite, everything can be done quite explicitly. I'm not going to go to more application of this theory. You can read in, say, the 9th volume of the series of Landau and Lifshitz, where they compute different quantity. For example, the decay of a Nambu-Goldstone boson into 2 Nambu-Goldstone boson. You can compute everything using this theory. It's not only a nice theory, but also predictive theory. Yeah.
Should I think of this as some gauging of like a Bargmann group or something like that? Like in the sense that you want you actually want the central extension of the Galilean group by the mass when you do the relativistic, just from the commutation relation. Is this what's going on behind the scenes, or?
It looks, yeah, it sounds like it is, but my math is not strong enough to be sure I can answer your question in definite way. Yes.
So your action, right, has dynamic. It does have dynamical gauge field, right?
No, my action has background gauge field. Yeah. I don't turn on dynamics of this A or dynamics of the metric. These are just probe quantities that one put in order to define the conserved current.
Are you asking it to respect the Galilei symmetry also?
I want to turn on the coupling of A mu to and G mu to the action, and then ask, what are the symmetry that I get? What are the symmetry? Right? This is a symmetry that I observed. If one observes that this theory, microscopic theory, has a certain symmetry, then it's useful in the infrared.
I have an intuition for why the transformation of the vector potential depends on time direction.
Yeah. It's a certain intuition that I have to it's maybe I should think a little bit more, because it's more like a feeling rather than intuition. Under a Galilean boost, basically this one, a Galilean boost corresponds to this parameter psi to be a linear function of time. So here you have a m times v, roughly speaking, shape of the A. Yeah. Yeah. So how would I say, it has a dual role. It's coupled to the momentum density, and it's also coupled to the current, to the spatial part of the current. Because of its dual role, it says that the momentum density and the U1 currents are the same quantity up to m.
With stress tensor, you could couple it to this metric, spatial metric GIJ. Right? And if you want to compute the current, you can couple it to the gauge field. But if you want to compute energy current, it seems like you don't have any geometric object that you can couple the energy current.
Yeah, so you can. So it's a slightly more complicated things that I was trying to avoid because so in order to compute it to couple to the current, we need to include a new set of gauge field. Turn out that this set of gauge field is the it's called the Latinger potential. Latinger potential that coupled to the energy and the in the some spatial components of that Latinger potential. And one can do it in a way that's a little bit more complicated than I wrote here. One again see that's the transformation. So the way that I would write here is the following. Let me maybe denote what would change. What would change here is that I have to replace this covariant derivative to a covariant linear combination of covariant derivative in space and time, where the C is the gauge field of the new gauge field, and I have to insert here e to minus phi, compensate e plus phi, something like that. And then you can work out the algebra and see that you get interesting things like the rate of the change of energy is equal to the product of electric field and the current. You get this ohmic heat from as a consequence of the Watt identity. The reference, you can look at that in the paper that I wrote. So the author is Son and I think Goldgar. It's one of the papers that we wrote some time ago. Some long time ago that I don't remember which year. Yeah. Okay. Any more question?
Just one small. So if I do a relativistic version directly and then take the small velocity expansion, do I get this?
Yeah, you can do that. You mean can you get this transformation? Yes, you do get that. If we take let me try to make it clear. So when you do relativistic theory, you find that in the non-relative, so you take the relativistic complex scalar field and then couple it to G mu nu and A mu. And then take the non-relativistic limit. You find that in the non-relativistic limit, phi is coupled not to G0i and AI separately, but it coupled to only a certain linear combination of G0i and AI. It's only a certain linear combination appear in the action. And that means that when you differentiate the action with respect to G0i and with respect to AI, you get the same thing. So you automatically see that Galilean invariance that appears. Yeah. If there is any question, you can always come to me and then we can discuss.
there a similar relationship between the stress energy transfer and the current in a relativistic theory or?
Yeah, in the relativistic theory, you have something that is implicit. The stress energy tensor is symmetric. And so the momentum density, which is T0I, is equal to the flux of energy, which Ti0 is equal to T0I. The flux of energy is equal to the momentum density. That's here, because we have taken the non-relativistic limit in the energy flux. When we call the energy flux, we have already taken out the. Let's see. Maybe it's actually this one. If you take the energy flux, is mostly the flux of the rest mass of the particle. So yeah, the rest mass is, so that is the, so the energy flux is just the mass times the current. So that's, roughly speaking, that's how you get. Yeah.
Here, by coupling to the background metric and the U1 gauge field, I also see that the energy density is proportional to air mass time. Is that statement that the energy density is proportional to the particle density?
So this is one has to be to separate out from the point of view of our non-relativistic world. Right? There is mass and there is energy, and only when we go to relativistic theory, they would combine into the total energy. So here, in this non-relativistic theory, there are two separate conserved quantities: the particle number density or the mass density and the energy density. They are separate. Okay, yeah. Okay, so next time we are going to discuss fermions.